on IoT systems are becoming increasingly large and complex, encompassing a wide range of methods that threaten the integrity, confidentiality, and availability of digital environments. Despite their effectiveness, modern IDS/IPS systems have a number of significant limitations. Ergo, it is becoming increasingly important to explore alternative solutions that are lighter, more energy efficient, easier to maintain, and less dependent on complex architectures that can provide a basic but reliable level of protection without overloading the system. This study proposes a formalized approach to representing incoming traffic in the form of signatures, which allows for accurate packet classification in ICS networks. Each signature is described by a multi-component tuple. Based on this representation, a hybrid method for detecting abnormal traffic has been developed, consisting of 3 blocks: signature classification by features, self-similarity analysis, and fuzzy inference. One of the fragments of the proposed model is the formation of signatures that describe each individual network packet through a set of its features. The incoming traffic is represented as a set of signatures: 1, where DI, element of the set, input generated signature, I, initial value, ND, number of elements of the input signatures set. The packet signature will allow you to uniquely identify the source of the traffic that initiates it, determine the size of the packet and the time when it was analyzed. The packet signature will be represented as a multi-component tuple, 2, where K, number of components in the tuple. Each generated signature will belong to the set D. The next part of the model is the process of classifying traffic by features to classify traffic into allowed, forbidden, and requiring further analysis using sets of allowed, forbidden, and undefined signatures. Represent the set of allowed signatures as follows: 3, where NG, number of allowed signatures. DI, signature assigned to the set of allowed signatures. Let's represent the set of forbidden signatures as follows: 4, where NB, number of forbidden signatures. DI, signature assigned to the set of forbidden signatures. Represent the set of undefined signatures as follows: 5, where new, number of undefined signatures. DI, signature that is assigned to the set of undefined signatures. The process of traffic classification based on signature analysis is represented as a partitioning of the set D, where DJ, the signature of the incoming traffic being analyzed. Next, we will describe a fragment of the traffic classification process based on self-similarity, which involves the use of a similarity metric between new signatures and previously verified ones that are part of the set of allowed ones. By analyzing consecutive time intervals, it is possible to verify new signatures based on previously obtained data, providing a dynamic update of the authorized traffic profile without the need to completely review the accumulated records. To quantify the degree of self-similarity, the Hurst coefficient is used to determine the level of correlation between the characteristics of signatures. Thanks to the self-similarity property, the amount of traffic that remains undetected is significantly reduced, thereby optimizing the monitoring process and increasing the overall efficiency of the anomaly detection system. To take into account traffic self-similarity, we define the following time parameters: T1, T3, the time interval for analyzing signatures for self-similarity, consisting of 2 sub-intervals. T1, T2, the time interval of signatures previously analyzed for self-similarity. T2, T3, the time interval of new signatures. Define the set M of signatures previously analyzed for self-similarity, and the set M of new signatures that have not been analyzed for self-similarity before, where DI7 time of receipt of the package for inspection. Define the similarity function. To determine the similarity of a packet signature to a set of previously defined packet signatures, we define the function Sn of the standard deviation. The function Rn, range of the accumulated deviation of the function, and determine the Hurst coefficient for each component of the tuple. Define the Hurst coefficient for the packet signature as the average of the Hurst coefficients for each component of the tuple. After the analysis is completed, the set DU will contain signatures that are undefined or different from the allowed signatures and require further analysis. To unambiguously classify the signatures left over from the previous stages, we will use the process of fuzzy detection of abnormal traffic. The structural organization of the fuzzy inference system for classifying the features of signature elements involves the integration of the following main components: Fuzzification. Membership functions, fuzzy inference mechanism, and defuzzification. The process of fuzzification provides transformation of deterministic input data into fuzzy terms to account for possible undefined uncertainties in the input characteristics. An example is given on the slide. As a result of the system's operation, the output variable result is formed, which takes on one of two intervals: allowed, from 0 to 50, or forbidden, from 50 to 100. If the signature is classified as allowed, the data is transmitted, and the signature is registered in the database of allowed connections. If the signature is identified as forbidden, the system blocks the connection by the source IP and MAC addresses, and the corresponding signature is added to the register of forbidden connections. We propose a hybrid method for detecting abnormal traffic which combines the advantages of several approaches: signature classification, self-similarity analysis, and fuzzy inference. Such a multi-level structure provides more accurate, reliable, and adaptive anomaly detection, reducing the number of undefined cases and optimizing security system resources. The input data are packets from the original data stream, a set of original signatures, D, the set of allowed signatures, DG, a set of forbidden signatures, DB, a set of undefined signatures, DU. Time intervals of the reference sample and the verification sample, a list of rules. The steps of the method are as follows. Step 1 to 4. Initialization. Step 5. Forming a packet signature DJ from the original data stream, D, that you want to check. Step 6. Performing the traffic classification method by features. If the signature is classified, you go to step 7. Otherwise, you go to step 9. Step 7. If you need to continue checking the signatures, you go to step 5. Otherwise, you go to step 8. Step 8. Finish the work. Step 9. Perform the traffic classification method based on self-similarity. If the signature is classified, you go to step 7. Otherwise, you go to step 10. Step 10. Performing a fuzzy method for detecting abnormal traffic. Go to step 7. The result of the work is an unambiguous classification of signatures as allowed or abnormal. Slide shows a diagram of data interaction in the hybrid method for detecting abnormal traffic. The set of initial data, D, is the source of input information for the traffic classification block by features. Also, the input data for this method is the set of forbidden signatures, DB, and the set of allowed signatures, DG. The result of the method is a set of undefined signatures, DU. The input to the traffic classification block based on self-similarity is a set of allowed signatures, DG, and a set of undefined signatures, DU. As a result of the block operation, the signatures are written to the set of allowed signatures, DG, and are removed from the set of undefined signatures, DU, or the sets remain unchanged. The input data for the fuzzy method of detecting abnormal traffic is a set of undefined signatures, DU, and a set of rules. As a result, the signature method from the set of undefined signatures, DU, classifies and overwrites to the set of forbidden signatures, DB, or a set of allowed signatures, DG, by removing them from the set of undefined signatures, DU. General requirements for the efficiency of solving the problem solved by an anomaly detection system can be expressed through the following well-known and frequently used quality metrics: true positive, false positive, true negative, false negative. Table illustrates the results of testing the developed method using two different datasets, WSNDS and CIC-IoT 2023. The results obtained indicate the high efficiency of the proposed method in processing both medium and large volumes of network traffic typical of Internet of Things, IoT, systems. Slide provides a comparative characterization of the performance of the hybrid method for detecting abnormal traffic based on the WSNDS and CIC-IoT 2023 datasets, evaluating it by key metrics: accuracy, positive prediction accuracy, recall, and F1 measure.